Okay, so picture this. A robot powers on for the very first time. It's got a perfect, detailed map of its surroundings. But there's one tiny problem. It has absolutely no clue where it is on that map. So how does it figure it out? Well, the answer is this really clever algorithm that can turn thousands of wild guesses into one single, totally confident answer. And that's the big question, right? This isn't just about getting from point A to point B. It's about figuring out where point A even is, with nothing to go on but a map and its own sensors. It sounds like a massive, almost impossible challenge, but as you're about to see, the solution is surprisingly beautiful. So let's meet our robot. It's staring down what engineers call the localization problem. I mean, it's online, it can see the walls and doors around it, and it has this perfect blueprint. But connecting what its sensors are seeing to one specific spot on that blueprint? Yeah, that's the really tricky part. Alright, so here's our game plan. First, we're going to lay out the problem. Then, we'll look at a brute force approach and see why it just doesn't work. After that, we'll meet the hero of our story, the particle filter. We'll walk through its process, see it in action, and then we'll talk about where else this amazing idea shows up. Okay, first things first. Let's really nail down what this robot is trying to accomplish. What's the actual challenge here? You know, at its heart, the task is pretty straightforward. The robot's got sensors, maybe a laser, maybe a camera, and it takes a little snapshot of what's around it. Then it just has to look at its big map and ask itself, okay, where in the world would I have to be standing for the room to look exactly like this? So, if it's just a matching game, what's the big deal? Well, it's not the comparison that's hard. It's the scale. The sheer, mind-boggling scale of it. A normal map could have thousands, maybe even millions, of possible places the robot could be. Your first instinct might be to just brute force it, right? Let's just treat the map like a giant sheet of graph paper. We could try to calculate a probability for every single square on that map. But just imagine a big warehouse or an office building. The number of squares you need to track becomes absolutely astronomical. And that's where we hit a really fundamental wall in computer science. This quote from the source material says it all. Sometimes the number of possibilities, that's the X here, is just way too big to handle. Trying to calculate the exact answer for every single spot on the map, it's just computationally impossible most of the time. So, if we can't track every single spot, what do? We take a shortcut, a really clever one. Instead of trying to track every possibility, we're just going to make a bunch of educated guesses. And that is the whole idea behind particle filtering. And each one of these little guesses has a name. We call it a particle. Now, a particle isn't a physical thing, it's just an idea, a hypothesis. It's one single guess, like, maybe the robot is at coordinate 3,3. That's one particle. So, a particle filter is basically just a system for managing a whole cloud of these guesses. It's not an exact solution, it's an approximation, but it's a super powerful one. Instead of the whole map, we just keep track of, say, 1,000 of these particles. And here's the key. Our confidence in where the robot is comes from where the particles are bunched up. If you see a big cluster of them in one hallway, we're pretty sure the robot's in that hallway. And you know what's so cool about this? When you actually look under the hood in the computer's memory, this whole sophisticated algorithm is just a list of coordinates. That's it. Each one of these little pairs of numbers is one particle, one single guess about where our robot might be. Okay, so how do we get from a big, random cloud of guesses to the one correct answer? Well, the algorithm has this rhythm, this simple repeating cycle that's constantly making the guesses better and better. I like to call it the three-step dance. And here are the steps. 1. Elapsed time, that's for movement. 2. Observe, that's when we use our sensors. And 3. Resample, which is where we get smart and focus on the best guesses. And this cycle just happens again and again and again. Alright, let's dive into step 1. Elapsed time. Now, when the robot moves, its motors aren't perfect, right? The wheels might slip a tiny bit. The floor might be bumpy. To account for all that real-world messiness, we take every single one of our particles, every guess, and we move it a little bit, adding just a touch of randomness. And you can see exactly what happens here. The before list of particles becomes the after list. Each guess is just wiggled a little bit. The overall effect is that our cloud of guesses spreads out and gets a little fuzzy, which totally makes sense. When you move without looking, you get a little more uncertain about your exact position. Okay, now for the magic. Step 2. Observe. This is where the robot actually uses its sensors to look at the world. It gets a real piece of data, a real clue, like, hey, I see a wall 2 meters ahead. And this is the crucial evidence we're going to use to get rid of all our bad guesses. So how do we use that evidence? This is the secret sauce. We go through every single one of our particles and give it a score, or a weight. And that score just answers a simple question. If the robot were really at this particle's location, how likely is it that it would see a wall 2 meters away? If the guess matches the data, boom, it gets a high score. If it doesn't, it gets a terrible score. And the result is our simple list of coordinates now has a score next to each one. So a particle that's a good fit gets a high weight, like 0.9. Another one that's a bad fit gets a low weight, like 0.2. We've just used math to sort our good guesses from our bad ones. But we're not quite done. We've got a list of scored guesses, but we still have all of them, good and bad. The final step, resampling, is where we focus our brain power on the guesses that actually matter. It's basically a game of survival of the fittest for our particles. Here's how it works. We create a brand new list of particles from scratch, and to fill it up, we randomly pick particles from our old scored list. But, and this is the key, it's a weighted lottery. Particles with higher scores have way more lottery tickets, so the good guesses get picked again and again, they get cloned. And the bad guesses with low scores, they probably don't get picked at all, they just disappear. And that's the whole cycle. Elapse, observe, resample. Now let's see what happens when the robot does this over and over and over as it starts to move around. Just watch this. Initially, the particles, those red dots, are spread everywhere. Total chaos. The robot has no idea where it is. But as it starts to move, and that three-step dance repeats, you see the clouds start to shrink. Particles in the wrong places get low scores and die off. Particles near the real location get high scores and multiply. And eventually, boom, the entire cloud converges into one tiny tight cluster right where the robot actually is. It has found itself. And what's so incredible is that this powerful idea of using a cloud of smart guesses to solve an impossibly big problem, it's not just for robots. This technique is used everywhere. I'm talking weather forecasting, financial modeling, even tracking objects in videos. It's a general-purpose tool for finding a tiny signal in a whole lot of noise. And that kind of leaves us with one big thought, doesn't it? The core idea here was to replace an exact but totally impossible calculation with a clever, approximate one that actually works. And it makes you wonder, what other huge, impossibly complex problems could we start to tackle, not by trying to solve them perfectly, but just by learning how to make and refine a few thousand really smart guesses?